Swayam Prabha. Digital India. Educated India.
Continuing our discussion on semiconductor device physics, in the last lecture we started our discussion on carrier generation. We looked at three ways of generating carriers: thermal, optical generation and electrical generation. And we also looked at recombination, where it could, depending on whether the material is direct semiconductor or indirect semiconductor, it can lead to radiative emission, in other words light emission, or non-radiative emission. And characteristics of all the generation recombination processes that we discussed so far was that they were band to band transition. Basically, so far we discussed that if I have a semiconductor which has conduction band and valence band, then we talked about an electron being promoted to the conduction band and leaving behind a hole. This is a generation process. And we also talked about combining with a hole in the valence band, and this is the recombination process. And we saw how it can happen, that is basically by thermal generation or optical generation or recombination, which result in light emission or non-radiative emission, which is basically heat. And the characteristic of this was that we were talking about all transition which were band to band, from valence band to conduction band or vice versa, band to band recombination generation processes. But this is not the only way to generate a electron hole pair or to recombine an electron hole pair. There are many more ways of doing it, and today's lecture is about talking about different ways of having recombination generation processes. So, today we are going to talk about different processes for different RG processes that are different from band to band transition. And then we will look at, we have already looked at the generation rate in the case of thermal or optical generation. We will also look at what would be recombination rate expression in couple of special cases of electron hole pair generation and recombination. So, let us start with different RG processes. We will first start with recombination processes and then find the equivalent of a generation process for each of the recombination mechanisms that exist. So, assuming that the first process is already discussed, band to band transition, let us look at the second way of having in a semiconductor, and that is known as RG center recombination. Now, before I answer that, I think it requires that we explain what is a RG center. What is a RG center? You have already studied in earlier modules that in order to make a intrinsic semiconductor extrinsic, we put some dopants which act either as donors or acceptors, and they contribute electrons and holes by thermal excitation to conduction or valence band. RG centers are also impurities but the difference between RG center and donor and acceptors is that donors and acceptor exist very close to the respective band edge. On the other hand, the impurities which create states rather deep in the mid gap, which create mid gap energy states. Now, these impurities which exist in the semiconductor cannot act as dopant, because the difference between the energy level and the band edge, respective band edge, is too large, but they act as a RG center. and they act RG as a recombination or generation center. How do they act as recombination center? If we see this only RG center in this case, then RG center which exists in the middle of the band gap, electron can come to the defect state, from where it can further go down and annihilate a hole. So, it is a two-step process now, which was earlier one step from conduction band to valence band. Now, it has become from conduction band to the recombination RG center, which is the impurity energy level, and then to the valence band. This process can also be seen as in two steps, in one which is it's basically same thing how you write it. Electron comes to the defect state or RG level, and a hole also combines at this level, and there that is where they annihilate each other. So, this defect state, the impurity state, acts as an intermediary in the recombination process, and this process in general does not give out light, it will give out heat, or it will be non-radiative. For this reason that it is a indirect thermal recombination, this process is also called as indirect thermal recombination. Direct thermal recombination being the process where band to band transition takes place. It also has another name, it is often called SRH centers. RG centers are also called SRH centers. SRH stands for the name of the three scientists, Shockley, Reed, and Hall, and they were the first one to explain this mechanism of recombination. Earlier we knew about the recombination from the conduction band to the valence band, and they proposed that the impurity centers which are in the mid gap can act as recombination generation center and create a path which will be non-radiative for recombination. Then we can talk about another process for recombination, and this is known as recombination via shallow levels. As you know, shallow levels are same as your donor or acceptor levels, and they can also contribute to the RG processes, to the recombination process. So, if you have for example, a donor sitting very close to the conduction band, it is possible that the electron first comes to the donor level, and then from there it interacts with the hole in the valence band and has a recombination process. Another option for that is also possible, that one has a acceptor level EA, and that can participate in the recombination, where electron first comes to the acceptor level, and from here it goes to the valence band, and there is a recombination process taking place this way. There can be other combinations of it also possible, where you have two levels, the electron is captured here, the hole is captured by the acceptor level, and then finally there is a recombination event taking place here. So, there can be many combinations of involvement of the shallow levels, which are basically your donor acceptor levels, which contribute to the carrier concentration in the semiconductor. And in this process, compared to the mid gap, is that many of these recombinations in the shallow levels is going to be radiative in nature. They can, all these large energy transitions can have radiative emission. So, shallow level centers in general are, maybe one can call them inefficient RG centers in terms of providing recombination. So, they are inefficient RG centers. Why are they inefficient? Because the chances that an electron which is captured by a donor level, it has two possibilities. It can either go back because of thermal fluctuations, go back to the conduction level, or it can recombine with the valence band. And then since this level difference is very, very small, it is very likely that it will come out of the donor level and be part of the conduction band. And hence the probability that it does the recombination via this route is very, very small, and that is why we are calling it a very inefficient RG centers, which are, if electron is trapped in a mid gap level, would generally recombine. We also find that it is radiative, as we have already mentioned, and but these processes generally which are involving shallow levels, their probability is very, very low at room temperature. So the rates are not very high. Probability for this recombination via shallow levels, probability is very low. So this is not a dominant recombination process if we are looking at the recombination of carriers. Now in the same series, then the next recombination mechanism is known as recombination. Involving excitons. Now again, before we explain this behavior, it is important to realize what are excitons. So once again, if we look at free electron in the conduction band and free hole in the valence band, they can move on their own, they are not bound to each other. But it can happen that a electron in the conduction band gets bound to a hole in the valence band. In that case, they are no more independent, rather they move as a whole, and that entity, electron hole pair which is bound to each other, is called exciton. And to represent this exciton, we say that this is a electron which has become part bound to the hole. Its level is slightly lower than the band edge of the conduction, and since this is not a real level, this is a level created because of formation of exciton, it is normally represented as in the bracket. Remember, all the levels which were there due to impurities were shown as the energy levels in the band gap. Now this electron which is bound to this hole can recombine and give emission. Once again, this emission is generally radiative in nature, and it can also participate through shallow levels. In other words, there can be a shallow level and a hole bound to not the electron here, but the electron in the shallow level or in the donor level. In this case, this exciton which is bound to the electron in the donor level is known as the bound exciton. As opposed to the exciton which is by bonding of the free electron and free hole in the valence band, this one is bound to the particular donor level and it cannot move freely. So there are two types of excitons. One is free exciton which will move together, electron hole pair will move, and the second type which is a bound exciton which cannot move freely in the material, but it can still recombine, and the electron will recombine with the hole here, and there will be annihilation, and again this will be radiative in nature. And this way one can think of more permutation combinations for recombination involving excitons. What are the observations about these recombination using excitons? As we can see, because of this binding energy of exciton, the emission that we get is not going to be equal to the emission of the band to band transition. It is going to be a emission which is going to be in sub band gap. So the energy of emission is going to be in sub band gap, and this is also another way of trying to figure out what is the binding energy of exciton is. And normally these processes through the exciton formation are important. These are the dominant processes at low temperature, not at room temperature. And majority of LEDs which one sees today, this is the major light producing mechanism. So, that brings us to the next recombination mechanism, and this is called OJ recombination. The R is silent and it is spelled as OJ, and in this process basically we have an electron and which is at a very high energy, and it has a collision with another electron. At the same time it recombines with a hole, and the energy that it generates in this process of recombination, it gives to the other electron, and the energy of that electron goes to a higher kinetic energy level, and that energy then will get reduced in steps, basically being lost as heat to the lattice, and then the second electron comes back to its ground state. In this process, the recombination energy is given to the second electron that is having a collision simultaneously with the recombination process. It takes the energy of the recombination process and loses it to the heat. So, the energy is lost in a non-radiative emission in this case, and we do not get any light here. It is basically taking place because of carrier collisions, and hence the process is normally occurring where you have high carrier concentration. Then these processes have to be accounted for. High carrier concentration basically means very high level of doping in the device, then this has to be accounted for in this case. So, in summary, what we have shown is, in addition to band transition, you can have recombination of carriers through various radiative or non-radiative mechanisms. First one being recombination via RG centers, which are impurity centers. Second one being recombination via shallow impurity levels. Third one being recombination due to excitons. Fourth one being recombination due to excitons, and the fifth one being recombination due to OJ processes, which are again non-radiative. Now, equivalent of this recombination process, because generation is exactly opposite of recombination, one can then talk about generation processes which can also occur in the material. So, if we look at these generation processes, just like we have RG center recombination, we can have RG center generation. So, after band to band generation, this would be RG center generation. And what do we have here is reverse of recombination, taking help of the RG centers. So, a whole electron which is in the valence band first goes to the RG centers, then from here it goes to the conduction band, leaving behind a hole, and this is the generation process. This can happen just like in the band to band transition. It can happen due to thermal generation. It can also happen due to light absorption. Light absorption can also take an electron to the RG center level, and then another light absorption can take it to the conduction level, leaving behind a hole. So, there are two ways that one can have a generation of electron hole pairs through RG center this would be an example of optical generation. So, the process as you can see is exactly reverse of RG center recombination. The next recombination process that we had was through the shallow centers. Now, if we think of generation through the shallow centers, it is nothing but same as creating a N or P type material. So, there is no specific generation process through the shallow centers. It is basically contributing to changing the electrical conductivity of the material. Same thing about excitons, since there are no, we are creating EH pairs, there are no existing EH pair, there is no concept of exciton generation to start with. Excitons are created only after electron hole pairs are existing and they bind with each other to form an exciton. But we do have the opposite of the process, which is OJ process, and we call it generation. Via impact ionization. This is opposite to the OJ process, because in the OJ process the collision of two electrons led to the recombination energy of one electron being given to the second electron, and then that particular energy is lost in heat. In this case, we talk about the energy, the high kinetic energy of an electron having a collision with another electron, it loses its energy, and the second when it has a collision with the carrier, it takes the electron in the valence band and takes it to the conduction band, thereby creating a hole here. So, this particular electron has a collision with the, you can say the material lattice or another carrier, in which it loses its energy, and this energy is given to the electron in the valence band, and that is moved to conduction band, creating a hole. So, by this impact of carriers with each other or with the lattice, we have created a electron hole pair, and this is why it is called generation by impact ionization. This is a very important process, because this is the key process for where you have collision basically dependent on collision of highly energetic carriers with the crystal lattice. And this generates electron and hole pair. Now, this process is normally occurs at high field, because you need highly energetic carriers. It occurs at high field, and this is a process by which one can have multiplication of carriers. A single carrier, when it has been excited to high energy, has a collision with the lattice and creates more carriers. So, this is a process by which you can have multiplication of carriers by impact ionization. And this is what leads to then eventual what is called as an avalanche breakdown, which we will see later in devices. Basically, it is there that a single carrier is generating multiple carriers, and those multiple carriers then generate more carriers, thereby you suddenly have a high leakage current and the device fails. So, this process of generation via impact ionization is important from that point of view. Now, all these processes that we have discussed, in addition to what we discussed in the last lecture, can occur in a semiconductor all at the same time. But it is not important that how many are occurring. What is important is what is the rate at which they are occurring. They will all be occurring at a different rate, and generally if we look at our discussion earlier, what one finds it that if you have a a device which is a low field device, you have a low field device and non-degenerate semiconductor. So, basically we have ruled out OJ processes here and generation impact ionization. Then the dominant RG mechanisms in such devices is going to be, and we are talking about room temperature processes, the RG processes that dominate are band to band transition and RG center. Now, depending on the situation and the device, one will also have to see which one of this is dominant. For example, if we have a device which is direct semiconductor device, then the rate for band to band transition is much higher as discussed earlier, because there is no requirement for momentum conservation while having this transition. Band to band transition dominates. That does not mean that RG center is not taking place. All it says is that the rate at which band to band transition is taking place is higher than the RG center. On the other hand, if I have an indirect semiconductor, in that case RG center recombination generations dominate. And this is required because band to band transition, as we discussed earlier looking at the EK diagram, is very much less probable compared to the band to band transition, transition through the RG centers in indirect semiconductors. So, the dominant process which we commonly see among all the RG processes that are discussed in devices is band to band and RG center. So, now let us see what kind of recombinations rate we are going to get. So, in the last lecture we got an expression for generation rate. If it is a thermal generation rate, then it is a constant value only dependent on the temperature. If it is a optical generation rate, then we can calculate it depending on what is the wavelength of the light coming in, what is the absorption coefficient of the material. You can calculate what would be the generation rate. Now, let us see if we can give some values to the recombination rate. So, what would be the recombination rate in a semiconductor? So, we have discussed many processes, and we have also said that maybe one or two will dominate and rest may not be dominant in a particular material. So, in general, if I want to write the total recombination rate in a semiconductor, I can say that it will be addition of all the processes discussed. So, my recombination rate from the last lecture is some constant because of first mechanism, let us say it is band to band transition multiplied by the carrier concentration in the conduction and valence band, plus the rate due to the second process through the RG center, for example, again NP, plus the third process maybe due to excitons, and so on. I can add all the recombination generation processes that I have talked about, or maybe there are more, and I will get the total recombination rate. Now, as we discussed also that not all of them will play a dominant part. So, often what is done is one looks at only just the recombination, the dominant recombination mechanism, and simplifies the expression by looking at only the dominant recombination mechanism. But this does not mean that I am limiting myself, because since each of the mechanism is independent of each other, I can always add the rates as I have shown here. So, I am going to derive equation only for a simple one mechanism, but if I have more than one mechanism, I will just add the rates for each one individually. So, let us look at this situation. We will look at two special cases which occur very often in the device physics and try to get a expression for R. The first case is which is often seen, which is known as low level injection. Low level injection basically means that in equilibrium you have the material which has equilibrium concentration of electrons and holes, and we know that this is basically N naught P naught is equal to the intrinsic carrier concentration square. We create excess electron and holes, we generate excess electron and holes by any process, maybe optical, such that the new carrier concentration is N naught plus delta N, and this is P naught plus delta P. And if we are doing it by thermal or optical generation, we know that if the excess carriers are generated at T is equal to 0, then del N naught is equal to del P naught. And then in the recombination process, at every instant you are going to recombine one electron with one hole, which basically also means that delta N is always going to be delta P in this process. If there is no other process taking place, there is no losing of carriers by another means, then this should always be true. So, low level injection basically then means that the excess carriers which are generated at any time, the maximum being at T equal to 0, is always less than delta N or delta P, is always less than the majority carrier concentration. So, delta N P is always going to be less than P naught. This is majority carrier concentration for N type semiconductor. And this is for P type semiconductor. So, in this condition, if I try to see how what would be the recombination rate in this condition, I can write my equation. So, at T is equal to 0, I have created excess electrons and excess holes by a, let us say, optical excitation process, such that the two concentrations are same. Then at any time T, I am trying to look at how is the concentration of electrons changing with time T. I could always write it as how is the concentration changing of holes, because one electron will recombine with one hole. Now, this rate is going to be equal to the recombination, whichever mechanism, does not matter, the constant will change. So, a general any one mechanism B times N times P minus the generation rate. So, I only put in excess carrier at T is equal to 0. After that, the generation rate is G thermal. Now, from our earlier discussion, we know that G thermal, due to thermal means is nothing but if this is the only mechanism taking place due to in this process, is going to be N naught P naught. So, then I can write my expression and I will expand this. The carrier concentration at any time is carrier concentration in equilibrium plus the excess carrier concentration. The change in that as a function of time is equal to B, N can be extended further in terms of N naught plus delta N, P naught plus delta P, and from here I get this as B N naught. Now, I can simplify this N naught and P naught being two constants here. So, this would just reduce to change in the excess carrier concentration due to recombination process will be B Now, this can as you can will easily simplify, this will cancel with the thermal generation. This particular expression, since we have taken the assumption of a very low level of injection, it is going to be very small compared to these two expressions. So, we can drop that since this is negligible, and this will then reduce to, with our low level injection, will reduce to B P naught delta n plus n naught delta P. And since we have optical excitation and then recombination, we know that delta n at any time is equal to delta P. I can write this as B delta n P naught plus n naught. Now this is a familiar equation. This is a first order differential equation, which is a very well known solution, and we know at the condition at t is equal to 0, delta n is equal to delta n naught. With that, the solution for the above equation is delta n is equal to delta n naught exponential minus t over time constant known as lifetime. For the carriers, tau is nothing but 1 over the recombination rate constant times n naught plus P naught. So, this entity is known as the carrier lifetime, and it is very important in devices. It it is defining the rate of recombination for in this case we have taken any one particular process. If we have more than one recombination process, we will just add tau 1 the recombination rate for first and second and third process. So, this is what would be the equation for change in the excess carrier concentration. So, in this low level injection regime, then recombination rate, which is d n dt, which in this case is going to be d delta n over dt, you can see is nothing but delta n naught over tau, because delta n is delta n naught exponential minus t over tau. Delta n over tau. So, this is our recombination rate. One can further simplify this equation. What is lifetime tau here for a general case is 1 over B n naught plus P naught, but if we take a majority carrier n type device, you can see that P naught is going to be very small. Then the lifetime for carriers there is going to be 1 over B n naught, and if it is a P type semiconductor, then this lifetime will reduce to 1 over B P naught, because n naught is going to be very small compared to P naught. So, this is the example of recombination rate when we have low level of injection. This basically means if I am going to put in recombination rate due to different processes in any equation, I can write R is equal to delta n over tau. If I have more than one process, then I would write delta n over tau 1 plus delta n over tau 2 and so on and so forth. So, this would be the recombination rate due to various processes in a semiconductor. Now, let us look at the second situation, and that would be a high level of injection. So, if you have generation that leads to high level of excess carrier present in the material, then the condition there is for high level injection, one can also talk about it injection or excitation. Normally injection is used when you have electrical generation, but if there are other means, then one would call it high level excitation. In this particular case, the situation is such that the excess carriers that are generated are much greater than the total carrier concentration in equilibrium. Now, if this is the case, we start with our equation that was there earlier. So, dN over dt is equal to R times Np minus B times Np minus B times N naught P naught. And in now, if I have this condition, you can easily see that I cannot neglect delta N times delta P. The excess carrier concentration is very high. What I can neglect is N naught P naught, and in that situation, then this will result in, if I am looking only in terms of excess carrier concentration, d delta N dt is going to be equal to B times N naught delta P plus P naught delta N plus delta N delta P. Now, earlier we neglected this cannot be neglected anymore, and this is going to remain in the equation. And so, the rate of change, if we put in the condition delta N is equal to delta P, is going to be B times delta N naught plus P naught plus delta N square. Now, this is a equation that needs to be solved then for finding out what would be delta N in case of high level injection, and the solution for this equation exists as delta N as a function of t is nothing but 1 over B t plus delta N naught inverse. So, this is for high level injection, and then the rate for high level injection will be given by negative of d n dt or negative of B over B t plus delta N naught inverse square. So, now we have two recombination rates to be used in our equation, one for low level of injection and the other one for high level of injection. And if we are talking about LED, you can see that this injection rate luminescence from the material is proportional to the recombination rate. If it is radiative recombination process, then how much light you will get is going to be proportional to this recombination rate. So, this is from application point of view, but now we have two general expressions for recombination rate if you have only a single process existing. So, now what will happen if I have more than one processes existing, and some of them we know are radiative and others are non-radiative. And we have already looked at the processes which make them radiative and not non-radiative. In that case, my recombination rate, as I have just discussed, is going to be equal to, let us say I am talking about two type of processes, one being overall radiative, one being non-radiative. Looking at a low injection level, low excitation level will be delta N over tau radiative process plus delta N over tau non-radiative process. Looking at the rate equation for low level of excitation, now this is often people equate it to an effective lifetime and make it, call it tau delta N over tau effective, where basically 1 over tau effective is equal to tau NR tau R over tau NR plus tau R. Or if you want to reverse it, this is sometimes also written as the effective lifetime is 1 over tau R over 1 over plus 1 over tau NR. Now, this is an interesting equation to observe, because what it says is that if I have two processes in which the radiative process is equal to the non-radiative recombination process, then I am going to lose some of the light in heat and some will come out as light. But if for some reason the processes which are non-radiative become much faster, then I may have overall recombination rate which is going to kill any radiative emission. And hence this is the tau effective is an interesting parameter to tell about the efficiency of luminescence. If tau r is much less than the tau nr, then this is good for luminescence, and this would be a good LED material. So far what we have, I will just summarize what we have learned about generation recombination processes. We have looked at generation of electron and hole pairs through various mechanisms in semiconductor. It could be transition when electron goes from valence band directly to conduction band, being band to band transition. It could be a transition where electron goes to valence band via RG center. RG centers are basically impurities or impurity defect complexes, which are somewhere giving energy levels in the mid gap of the semiconductor. It can do recombination through excitons or through Auger process. Similarly, you can have generation via impact ionization, or you can have generation via RG centers. Then we looked at, we have already looked at generation rate in earlier lecture. Today we looked at in special cases what would be the recombination rate. A general expression for recombination rate was given as B times Np, and then we will define for each recombination process different rate constant. And then for two special cases we have shown for low level of excitation that recombination rate is nothing but delta n over tau, and where tau is given by 1 over B n naught plus B naught. For high level excitation, R will be given by negative of B over and anytime we need to use the recombination rate, depending on which situation is there, we can use these equation directly or use a general expression if we do not know whether the level of excitation is low or high. Generally in most of the device physics examples we will take up here, in simple devices we take the case of low level excitation and solve the equations. So now at the end of this lecture we have expressions for generation rate for electron hole